Let's review. The final arbiter of whether a process is thermodynamically favorable, i.e. spontaneous, in the left to right direction, as it is written in the reaction equation, is the change in Gibbs free energy. Delta G is equal to delta H minus T delta S. If delta G is less than 0, that is, if it's negative, thermodynamically favorable, left to right. If delta G is greater than 0, that is, positive, not thermodynamically favorable, left to right. If delta G equals 0, then we're at equilibrium. We see that the change in enthalpy, delta H, and the change in entropy, delta S, both play a role in determining spontaneity. Standard free energies of formation, which are designated delta GF naught, have been tabulated for pure solids, pure liquids, and gases at about 1 atmosphere of pressure and 1 molar solution. What's not written here is, of course, the temperature, which we know to be 25 degrees Celsius. For elements in their standard states, the standard free energy of formation is 0. This goes along with the heat of formation, the standard heat of formation for an element in its standard state. Those values, you might remember, are also 0. For a reaction, the standard free energy change is found by doing our products minus reactants scheme, which we learned earlier applies for changes in reaction enthalpy and also changes in reaction entropy. So it's the same idea in both of those cases as it is here. Remember that delta G says which way a reaction will proceed, but it says nothing about the reaction rate. When we calculate a delta G, if it comes out negative, we can say, yep, it's thermodynamically favorable left to right, but we have no idea as to how long it might take. It might move like a cheetah, it might move like a tortoise. Let's calculate the standard free energy change for this reaction. We're going to need our delta GF naught values, most of which we're going to have to look up. But let's think before we do that, are there any of them that are 0? And that would be yes, because Cl2 is the standard state of the element chlorine. The other two values we're going to have to look up. We can do that, no problem. And now we're going to use products minus reactants. All the coefficients in the equation are 1. We're going to go 1 mole of PCl5 multiplied by negative 324.6. Then on the reactant side, we can omit the chlorine because anything multiplied by 0 is still 0. So then we just need to include the PCl3 term. If we do that calculation, not forgetting the negative signs, we get negative 38.3 kilojoules. Now, what does this tell us? It tells us that this reaction is thermodynamically favorable, or spontaneous, as written, left to right. Does it tell us anything about the rate of the reaction? And the answer is no. If we look at this gentleman here in the lower left, we might say, oh, he's so spontaneous. We can see it right there. He is spontaneous. He's showed up with flowers. This guy on the right, you shouldn't be surprised if I tell you that he is spontaneous as well. But the rate of his reaction is somewhat different than the dude on the left. The value of delta G tells us whether a reaction is thermodynamically favorable, left to right, or whether it's not, but it tells us nothing about the rate.